All right, so we're starting this new section, and there's a what we're going to start today and work on through Friday. Is the overarching theme is going to be here, right? Synthesis and application of alkyl halides. And so we're going to discuss two methods of making alkyl halides. Not today. Today through Friday, we're only going to do the alcohols to alkyl halides. But we're going to discuss two methods. First, we're going to talk about converting alcohols into alkyl halides. And then the second method is using allylic bromination, right? But the overall section, we're going to talk about the synthesis part, how to make them through these two methods right here. And then the application part, we're going to talk about, I'll just write it here. We're going to talk about a couple of things. We're going to talk about organometallics. And substitution. Substitution and elimination. So let me just put that. Right, and how to use alkyl halides in those reactions. But first we need to talk about how to make them. And then once we talk about how to make them, then we will discuss how to use them. So that's this whole section. But the part that's on the exam, on our exam that's coming up, is only going to be the alcohols to alkyl halides. So let me add a page here, and then so I guess the question is, what is an alkyl halide, right? It's a type of functional group, but what do you think it is? Anybody? Right, so it is a type of functional group that we learned in part one. The alkyl part is exactly what it means. So let's say I have a chain, don't have to be many carbons, but a carbon chain. This is the alkyl part of the alkyl halide. Right, and then the halide part is exactly what it sounds like. There's a halogen somewhere in this structure. So let's just put a chlorine right here. Right, so when we say alkyl halide, that's what we mean. Like it's some alkyl chain that contains a halogen somewhere in the structure. Right, so it's a type of functional group. It has a lot of utility, basically because of the carbon halogen bond right here. So this bond right here. Hold up. Right, that carbon halogen bond is very reactive. So I can do a lot of different things there. Right, and some of the stuff that we're going to talk about, especially when we talk about organometallics, is we're going to talk about coupling reactions, how to take alkyl halides and couple them to other alkyl halides and make new carbon-carbon bonds. Right, so when we do that coupling, we're going to make new CC bonds. I'm just going to put that here. Right, and that's all a consequence of that carbon-chlorine bond being reactive like that. Another reaction that we're going to talk about that I already mentioned, but I'll say it again here, is substitution and elimination. That carbon-chlorine bond is very susceptible to substitution reactions. All right, any questions so far? So these alkyl halides are a very important class of functional groups. You use them for a lot of different stuff. So when we use alcohols to make them, this is one way to synthesize them, and it's a very facile method. And I need to move one of these pages up because I want to start with this reaction right here. So, there we go. All right, so we're going to talk about, let me just put another page here. We're going to talk about 3 ways to convert alcohols into alkyl halides today. Well, we won't get to all 3 today, but this week. Right, 3 methods. And if you watch the video that I sent out dealing with converting alcohols to alkyl halides, what's the one thing that you have to do? Let me say this. So how about, let's say I have an alcohol here and I want to convert that into this, right? So this is my alcohol. This is my alkyl halide. The bromine is the halogen, so that's why it's an alkyl halide. What do I need to do? What's the one thing that you have to do to the OH group in order to get this type of reaction to happen? If you watch that video that I sent on Friday. Or let me back up. What happened in this reaction? What type of reaction happened? Well, not even say type. What happened here? Anybody?
Which was substituted for bromine.
I did a substitute. So that's great. Thank you. All of these reactions are substitutions. Right. Every alcohol conversion into an alkyl halide is a substitution reaction. Right. And in a substitution, if you remember from part 1, there are 2 types, SN2 or SN1. And what you need in a substitution is a substrate and a nucleophile, right? Substrate, nucleophile. The substrate in this case is the alcohol. The nucleophile in this case is going to be the halogen. Right, and that halogen is going to substitute for the alcohol. What is the OH group in this particular reaction, this substitution reaction? What would we call that? You should remember that from part 1. That's part of that working knowledge. What do we call the OH group here?
Is it the leaving group?
It's the leaving group. Excellent. Every substitution has these components. You have a substrate that contains the leaving group. You have a nucleophile that comes in and knocks out the leaving group. And it either happens via SN2 or SN1 pathway. Right? All substitutions happen like this. There was another thing I wanted to ask. Oh, okay. So the OH is the leaving group, or LG. I'm abbreviating that in the substitution. And basically the leaving group itself is going to control the rate of the reaction in this case. And so if it's a good leaving group, the reaction is going to be faster. If it's a bad leaving group, the reaction is going to be slower. So OH is actually a terrible leaving group. And there's a way to determine like the quality of a leaving group. Anybody remember that from part 1? Did we talk about that in part 1?
pKa values.
Come on, man. That's exactly right. The pKa value of the conjugate acid. So we're going to say leaving group quality is based on pKa of the conjugate acid of the leaving group. Right? If you remember when we studied pKa, the conjugate acid is whatever the well, there are a couple of ways to define that, but in this case, the conjugate acid of OH is water. Right. So in the case of when we're doing substitution, the conjugate acid, it'll be whatever the leaving group is plus a proton. So you'll just add a proton to whatever that leaving group is. And that's how you know what conjugate acid or what acid to look up on that pKa list. And I didn't put it in this handout because we're going to study substitution and elimination in great detail in a couple of weeks. So, but we did touch it in part 1. So if we have questions, you can ask them now, because maybe if you took Dr. Abdallah, y'all may not have touched substitution and elimination in a detailed way. So if you have questions, you can ask them now. Right. So working knowledge wise, thinking about going forward with these reactions, working knowledge wise, you need to know the difference between SN2 and SN1, which we'll talk about, and I'm happy to discuss it. Right. You need to know what a nucleophile is from part 1, or remember what a nucleophile is. And you need to remember what pKa is, like what it measures. Right. It's actually a measure of acidity. And it's based on loosely how stable the conjugate base is of a particular acid. But we'll dig more into that later. All right. So one of the main things about this reaction that I went around the world to get to is that since OH is a bad leaving group, every one of these reactions is going to have one step in it where you convert OH into a better leaving group. Right. And that's in the video that I sent out. Every one of these reactions that we're going to talk about, the first step is always to make OH a better leaving group. Right. So every one of these reactions, because it's a bad leaving group, and the reaction without converting it to something better, the reaction won't happen. It'll just sit. You may get a little bit of reactivity, but not a lot. Right. Any questions before we move to this first reaction with converting alcohols into alkyl halides? And I will post these notes. I'm going to have to shrink this down a little bit, the text, because otherwise when I print it as a PDF, it's going to be crappy looking. So, but I'll clean it up before I post it. All right. Any questions about anything so far? We got more people now, so I'm gonna put this handout in again in the chat. If you're on a device, a phone, you're not gonna be able to see it. If you're on a laptop or a tablet, I think you'll be able to see it. All right, so let's look at the first reaction then. And this is what we're gonna do is look at the overall reaction and talk about the details of the reaction. So the first reaction that we're going to look at is here, where we take an alcohol plus an acid. HX is my acid. Right. So the acid is going to be the source of my halogen. And then the alcohol, of course, is my substrate. So this is going to be, again, it's a substitution where if you don't even look at we're going to go through the mechanism as well. But even if you don't look at the outcome, the product, right, where's the substitution going to happen? right? We know already that that's my leaving group. What is going to replace that? Let's just say that first and see if we can predict the product before we go through how we get to the product. All right, so it's this, the I down here is what's going to replace OH. So this is going to be my nucleophile, and OH, of course, is my leaving group. So I'm really kind of sliding in a little bit of substitution here already. And then we'll talk in more detail about it later. Right? So the product is over here. Right? You can see right here the iodine replaced OH, and then this is plus, and you can put this on your handout, H2O. Right? Water is a side product. Because I know sometimes when you don't see everything at the end, and you kind of it kind of throws it off because you want to keep track of all the atoms and stuff like that. So you can add the water in right there. Right. So now let's go to how this happens, the mechanism. All right. So the first step in the mechanism, if you look at this intermediate, what does it look like happen? Going from the alcohol to that intermediate. And I'm going to put the I down here with the electrons around it. What does it look like happen to the OH group?
It added a hydrogen.
You added a hydrogen to it. So that first step, good, is what we call a proton transfer. That's something we talked about quite a bit. I know in my class we did when we were studying acids and bases, was a proton transfer. So a proton is just H plus, right? It's a hydrogen with no electrons, it's just H plus, right? So, and then when you have a proton transfer, you have to be able to show how that happened, right? And so the way you do that is anytime you're doing a mechanism, you have to show how something happened with curved arrows. I know we learned that in part 1. This is just an extension of that, right? So for proton transfer, it's this hydrogen right here that I'm after, right? So I'm going to just show that here. So I'm going to take a arrow going from OH, from a pair of electrons on OH to that proton, and I'm going to break the HI bond, give the electrons to iodine, right? If you recall from part 1, this is acid-base chemistry. Hold up. I got to be more specific in here. It's the bond between H and I that's breaking, right? And those electrons are going to iodine. That's how iodine now has 4 lone pairs around it over here. It has 3 over here, but in the intermediate stage, there are 4 because it picked up a pair of electrons from that HI bond. All right, so this is nucleophile, electrophile / acid-base chemistry. This is working knowledge. All right, so once I do that, that's how I get to here. And then if you notice, my OH group is no longer OH. Now it's water. Right? We have a special name for this when OH is, when that water is there and that oxygen has a positive charge. We call it a hydronium. right? This is an excellent leaving group. OH by itself is terrible. The hydronium is excellent. And if you want to know why it's excellent, the conjugate acid of that is H3O plus, right? I think the pKa of that is something like -3 or something like that, very low pKa. All right. As a matter of fact, can somebody Google that right quick? What the pKa of H3O plus is and tell us what it is. I know it's a negative number, or it's, at least it's very close to 0. All right, we're gonna
I
while
got
you're looking,
1.7.
say that again.
I got 1.7.
1.7. Yeah, I know it was a very low. This is it, and so what that means is that H3O plus is a very strong acid, right? That pKa that close to 0 is very strong acid. So that means that the conjugate base of that is stable. So the water, which would be the conjugate base of H3O plus, is neutral and is stable. We know that, right? Water is a very stable molecule. But the way you know that water is a great leaving group is by looking at the pKa of its conjugate acid, which would be that water plus another proton, which is H3O plus. All right, so we know that, right? That's the whole purpose of this first step, is to make OH a better leaving group. All right, and there are lots of ways to do that, but for this particular reaction, we do a proton transfer to make OH into a hydronium ion, which leaves readily. All right, so now over here, I'm going to go from the hydronium to a carbocation. All right, so this carbocation intermediate is a part of this mechanism anytime you use this method. Anytime you use HX to convert an alcohol into an alkyl halide, is going to go through a carbocation intermediate, right? Anytime. And so now you have this intermediate. How did I get there? From the hydronium intermediate. What did I do? And it's that plus the H2O over here on the side. So what happened?
You broke the bond between the oxygen and carbon.
Yeah, so I broke the CO bond. That's exactly right. And because oxygen has a plus charge, when I break that bond, those electrons in the bond are going with oxygen, right? You always break a bond. If this is working knowledge from part 1, anytime you break a bond between two atoms, the more electronegative atom takes the electrons, right? Anybody remember what type of bond breaking that is, where both electrons go with one atom? Remember that was lytic and genic, and it's either homo or hetero, homolytic or homogenic, heterolytic or heterogenic. Anybody remember that from part 1?
I think it's heterolytic.
Okay, great. It is. It's heterolytic cleavage. That's exactly right. Both electrons go with one atom, right? So it's heterolytic bond cleavage. And again, when you break a bond between two atoms, the electrons always go with the more electronegative atom, which in this case is oxygen. So that leaves this carbon positively charged, right? And keep in mind, this iodine is just down here lurking, waiting for an opportunity to come in and react with that carbon, right? Let me pause right here. Any questions about anything that we've talked about so far? All right. So now I need to get to my product, and I should have. Well, never mind. Now I need to get to the product. How do I get here? I need to make a bond between iodine, and let me put those lone pairs back in. I need to make a bond between iodine and carbon. Iodine is my nucleophile. This is my electrophile. Every reaction that we study is going to be able, you'll be able to reduce it down to whether something is a nucleophile or an electrophile, or whether it's an acid or a base. How do I do that? Or how do I show it? The nucleophile reacting with the electrophile.
Draw an arrow from iodine to the positive carbon.
Like that?
Mm-hmm.
That's it, right? So once I do that, that's how I'll make that carbon iodine bond. And this is my product. Right. So I've taken a alcohol, which I started with, reacted it with an acid, HI in this case, and that can, we'll talk about that, what the halogen can be. And then in doing that, I've converted that alcohol into an alkyl halide. Right, questions about that? I'm gonna give you some details about this mechanism too, as far about this reaction, as far as like what's preferred. All right. And let's talk about this step right here. Right, the substitution step. So in this case, water is my leaving group, and water left before iodine came in. Right, iodine didn't come in and force the water out. Water left first, and then the iodine came in. What if you took part one and we talked about substitution and elimination? Which class does this fall under? Where your leaving group leaves first before your nucleophile comes in. Anybody remember that? Right, there are two classes of substitutions that we study, right? SN2 and SN1.
Is it SN1?
It is. This falls under the class of an SN1 substitution. Right, and the characteristic of a SN1 is a carbocation intermediate. So your leaving group leaves first. That's your rate determining step. Right, and then you form a carbocation, and then the nucleophile attacks. Right, those are the steps that happen in the SN1. So you're always going to have this carbocation intermediate before your nucleophile attacks. All right, so it is a SN1. Now this type, and that leads to another piece of information about this reaction, which is this, that this is the preferred method brain is moving faster than my hand. It's the preferred method to convert tertiary alcohols, right? Secondaries work. This is a secondary alcohol right here, but it's the preferred for tertiary alcohol because it's SN1 and because it forms a carbocation, right? It's preferred for tertiary. Secondaries will work though. A little bit slower. Primaries are bad, right? They don't, a primary alcohol using this method, this is not the method you want to use on a primary alcohol. You want to pick something else. We'll talk about that in a second. So why do you think tertiaries work so well with this method? Looking at the overall mechanism and the fact that you form a carbocation. Anybody remember the trend from part 1, working knowledge for carbocation stability? How stable a carbocation is? All right, so what would be the most stable carbocation? If I made a carbocation on a carbon, I'll put a plus charge on a carbon. What's the most stable?
Here's a tertiary.
The tertiary. So that's why this method works best for tertiary alcohols, because when you get to the carbocation step where your leaving group leaves, you get a very stable carbocation. If you recall, a tertiary is more stable than a secondary, which is more stable than a primary, which is more stable than a methyl cation. Right. Now, let me ask this question, because it may be quiet because you may not remember what primary, secondary, and tertiary is. Is there anybody in that boat? Don't be ashamed to say that, and because I can show it.
Yes, could you show that, please?
Mm-hmm. So these are when we talk about a tertiary alcohol, that's tertiary, right? It's got 3 bonds to that. The carbon here, where your alcohol is, we call that a carbonyl. And that carbon has 3 carbons bonded to it. Right? And then a secondary alcohol is going to have 2 carbons bonded to it. To that carbon where your alcohol is. Put the carbonyl in a different color. So that central carbon where the OH is has 2 carbons attached to it. So it's secondary. And then a primary would be like this, right? Where this is your carbonyl, and then it has 1 carbon attached to it. And then of course, methyl would be like this with nothing but hydrogen attached. All right, so when we talk about tertiary, secondary, and primary, this is what we're talking about. How the alcohol itself is substituted. And I'll put that as a subheading down here. All right, so this alcohol right here is a secondary alcohol. Does that the central carbon where the OH is has two carbons bound to it. It's got a carbon on the left and on the right. So it's a secondary. All right. Any questions about that? So that matters, right? If it's a tertiary, it's going to be really fast. Secondary, it's going to slow down a bit. Primary is going to slow down to a crawl, and probably the mechanism is going to change from being SN1 to SN2. All right. Any questions? I want to take that other reaction and talk about the carbocation. Let me see if I can cut it. Or at least copy it and put it on another page. Let's talk about that. And then that's where we'll stop. Let's say it doesn't change mechanisms and it does go through a SN1. Let's answer this question about why it slows down. So what's the first step here? What are we doing? We're trying to convert this alcohol into an alkyl halide. What is the first step in this reaction? And what if you are stuck there, what was the first step here? Right? The alcohol actually attacked the acid and did a proton transfer. That's always the same. When you're doing alcohols to alkyl halides with HX as your halogen source, the first step is always going to be a proton transfer. So I'm going to attack here like that, and I'm going to break the HCl bond. Right? What do we get from that? This is going to be what? O, H, H, and that's that oxygen is positive plus chlorine, Cl minus. Right, now what? I have my hydronium ion, which is a good, it's a good leaving group. So I need to make this carbocation. How do I show that? And I'm abbreviating intermediate, by the way. Just being lazy. It's Monday. Anybody? How do I show that alcohol over the hydronium or the water leaving? What do I need to do?
Break the carbon oxygen bond.
Break the CO bond and give the electrons to oxygen. Always give the electrons to the more electronegative atom. Before I go further, is everybody okay with this carbon right here? Like, do you understand that this is a CH2? If not, say something.
No.
Okay. So remember when we do a skeletal form, all right, and let's say we have an atom here or whatever, it can be whatever atom bonded to that carbon. Every vertex in a skeletal form is a CH2. And then every terminus is a CH3, unless there's another atom there. All right, so when I break this bond right here, this is actually going to be this is going to be a CH2, and I'll write it out on the other side. So this is now CH2, and that's positive, plus water, plus chlorine. And that's minus, right? So tell me why this is bad using this method right here. What kind of carbocation is that? Is it primary? Is it secondary? Is it tertiary? So I have a carbon or carbocation. If I have 3 carbons attached to it, it's tertiary, right? If I have 2 carbons attached to it, it's secondary. You can see how this progression is going. If I have 1 carbon attached to it, it's primary. And if I have only hydrogens attached to it, call that a methyl carbocation. Right, so all of these carbocations are possible, but they're not all equally stable. The tertiary is the most stable, and then the methyl is the least. Brain is really tripping today. Right? So where does the primary fall in there? Is it bad or good? Based on how the trend is going. Where you go from the most stable being tertiary, and then secondary, and then primary, and then methyl. Right? What do you think? The methyl is the worst, primary is the second worst, right? So that's one thing in chemistry you never want to do is form a primary carbocation, right? It's not stable. It's very unstable. So up here, I'm forming a primary. Right? And that's not good. So that's going to really cause the rate of this reaction to slow down like tremendously.
I have a
That's why you
question.
don't- Go ahead.
So, which carbon are we looking at exactly?
The one where the OH is right here.
Okay, that's what I thought. Okay.
Mhm. So that carbon is primary, right? Because it only has one other bond to carbon. And so because of that, when you make it a carbocation, it's going to suck. Basically, it's the one of the suckiest carbocations that you can make. So if it goes through a mechanism like this where you have to lose your leaving group first, the rate is going to be trash, right? It's going to be very slow. So that's why this method is preferably used on tertiary alcohols, because when you lose that leaving group, the tertiary carbocation is more stable. All right, we're going to stop here. Any questions or any other questions about this or about anything? Okay, if not, we'll,
Sorry.
go ahead.
Yes, I just wanted to confirm. When is our first test again?
Friday, 27th.
Okay, just checking. Thank you.
No problem.
And the test will be over this and what we've learned earlier.
Yes.
Okay, thank you.
Mhm.
So I know that we turn in all of the work like the day after.
Yes.
Like I know that there's like 1 or 2 questions that we didn't do in class, so we do those on our own.
Which, you mean on the first handout?
Yeah, I think the last.
Yeah, the
Yeah.
last 2 questions on the handout with the mirror images and all that stuff on it.
Mm-hmm.
Yes. So once we'll go back to that. I will look at that on we'll look at it on Friday. But yeah, unless I specifically say on your own, then you don't have to do it, but we'll go back and do it. We'll go back and look, because those questions we should be able to answer based on what we talked about on Friday. But for future reference, any question that I want you to do outside of class that's on one of our handouts, I'll let you know ahead of time, like, hey, I want you to finish this in your own time or something like that.
Okay, thank you.
Good question. Other questions?